Alright guys, so this is polynomial functions, unit 5. So we're going to start with classifications. You guys have seen this before, but maybe you don't remember it. A lot of Algebra 1 in this unit, okay? So we have a word bank for you. We have some examples. So number of terms, let's start with this and how it's called. So here are the 4 different types. Does anyone know which one term would be? Anyone take a guess? Polynomial, monomial. Monomial. Monomial is 1. Monomial. What would be 2? Binomial. 3. Trinomial, like a tricycle, bless you. Trinomial. And 4 or more terms would be called a polynomial. Okay, and that's what this unit is. Okay. Now, what this means is when we're talking about a monomial, we're talking about one term, one piece. Okay? A term is separated by a plus or minus sign. Okay? So the example for a monomial would be 3x because that's just one term. Yes, it's a 3, yes, it's an x, but it's together. It's not separated by a plus or minus. Okay? Questions? Okay, so binomial would be 2 terms. Does anyone know which one that might be? 4x to the 5th minus 3. Yeah, 4x to the 5th minus 3. 2 terms separated by a minus sign. Okay, Austin, do you have the notes?
Yeah.
Trinomial would be 3 terms, so it would be the 2x. Excellent, Olivia. That one. And then the last one, polynomial, 4 or more terms. X to the 6th minus 3x to the 3rd plus 2x minus 5. Any questions on that? That should be quite simple, but anything that's like weird, doesn't make sense? Okay. This part down here, the classifying the single variable polynomial functions by degree, this is important. Okay? So notice that we have our parent functions. Whereas on the board, parent functions. Okay? F of x equals x. F of x equals x squared. Do you guys know which ones these are? We've already studied these. So what's f of x equals x? What do we call that? Linear, right? What about x to the 2nd? What type of function is that? Starts with a Q. Quadratic. Okay? So those are ones we've already learned so far. So you should know those. If you don't know those, that's a problem. So when it says degree, I know I'm kind of jumping around, but when it says degree, they're just looking at the exponent at the top. Okay? So what's the exponent right here? 1. What about the next one? X to the 2nd, 2. Degree, 3, 4, 5. Yes? So when they say degree, they're looking at the exponent. Alright, so we already know linear and quadratic. F of x equals x to the 3rd is called cubic. X to the 4th is called quartic. And x to the 5th is called quintic. And the way I memorize these is I just count on my hand to 5. So I remember what it is, and I say linear, quadratic, cubic, quartic, quintic. Linear, quadratic, cubic, quartic, quintic. Okay? What you'll see down here also are the parent graphs. Okay? So we already know linear is a straight line. On yours it's really bad, so you might need to retrace it. Okay? A quadratic, everyone knows it's a U. And then our cubic comes up from the bottom, kind of swirls through the origin, and continues up. We're going to see these. Okay? Quartic is very similar to a quadratic. Very similar. Okay? But it's just a little flatter, like where the vertex would be. Just a little flatter. And that's what you're going to start to notice, that our even functions look very much like a quadratic, but they just keep getting flatter at this part. Okay? Same thing with our odd functions. X to the third, we have this little squiggle here, but then when we have x to the fifth, the squiggle just gets a little flatter at the origin. What is that about? Okay? Any questions? Okay. Flip the page. Alright, polynomial functions. So, turning points. This is important. You might have heard us say this before, a turning point. Okay? You may have seen a function in the beginning of the year that we've given you that looks like this. Okay, we've asked you to do domain and range and all those graphical characteristics. Okay? We've told you about these points, and we've called them local maximums, local minimums, right? Sometimes when I have a quadratic function, what would be another name that I'd call that? Starts with a V? A vertex, okay? We also call it a turning point, okay? So a turning point could be defined as a change in direction. And what they mean by that is going from increasing to decreasing, or vice versa, Angel. Decreasing to increasing, okay? That point where it changes. Okay? Like we said, it's also a maximum or minimum. And we also call it a vertex. So it's all the same thing. Okay? But in this unit, it's very important. Okay. The maximum number of possible turns. Let's see if we can figure this out. How many turning points does this have? One turning point, right? It changes from decreasing to increasing. One turning point. What do we call this function? Quadratic. And does anyone remember what the parent function is? F of x equals x to the second. So the maximum number of possible turns should be one less than the degree. One less than the degree. So if this is x to the second, this would be one turning point or less. So we just write one less than the degree. And we're going to obviously explain this more in depth. What is going on? Is it messing with me?
No, I think it's because it's recording and my computer is a little slow.
Pick it up. Smartboard. All right. So everyone has a calculator, right? Yes. You guys awake? Yeah. One less than the degree. Okay, so like if the function is x to the second here, one less than the degree. So it should have one turning point. Okay, when they say maximum, it's the maximum amount. So if I have to the fourth, the maximum turning point I could have is 3. I could have one turning point, and you'll see that in some of these. Unless the Sawyer's changed. Okay, so this function, they want you to sketch it. Okay, so you can go ahead into the calculator. I'm scared to touch down here. Go into the calculator. How would I see what this function looks like? Go ahead and type it into y equals. Okay. Thank you. So we've got x squared plus x minus 2. And hit graph. Now Miss Sawyer's looks like she was doing some application stuff. So how do I get it to look like the standard screen? Zoom 6. You guys got to know that. Zoom 6. Okay? So it looks something like this. When we ask for a little sketch like this, it doesn't have to be perfect. Okay? So I'm not asking you to find the specific points. But on the test, if I'm asking you to sketch a function, Give me the vertex, give me the solutions. That's when I want to see specific points. Here, it's okay to just do a sketch of what you see. So I see the vertex kind of in this quadrant. Does anyone know what quadrant this is? Right there. So it looks something like that. That's okay. Right? Just a little sketch. Okay? Now, when we talk about the degree of an equation, see how the next column says degree from equation? It's quadratic. So I'm looking for the highest exponent. When they say degree, I'm looking for the highest exponent. Sometimes your teachers will try to trick you and put it out of order. Okay? But you gotta look for it. Sometimes on the SOL, not going to be in standard form. Standard form is when it decreases exponents. Okay? So what would be the degree of this equation? What's the highest degree? 2. So you just put 2. It's literally that simple. Okay? Thank you. Alright, and then number of turning points. You have to look at the graph. Because remember what we said, the maximum number of turning points would be 1 less than the degree. You guys are not awake right now. But in this picture, how many turning points do I have? 1. I'm going to show you an example where it doesn't come out so nice. Okay? So, Jeffrey, don't always assume that it's 1 less than the degree. Okay? It's the maximum number of turning points is 1 less than the degree. Okay? Why don't you guys try the next one without me? So go ahead, type the function in the calculator, sketch the graph, get the degree, and get the number of turning points. Go ahead, I'll give you 1 minute. And based on the graph, the number of turning points is how many? Does everyone see it? Where it changes direction here, and it changes direction here. Always going to see me put those dots there. Okay, so that's a good method just in case you're not sure. Alright, what about the next one? Guys, think you can get that one quickly? Put it in the calculator. X to the 4th. Make sure you guys are practicing how to type this stuff in because it's very easy to make a mistake when you do the exponent and not to push over.
Everybody knows how to do the exponent when it's higher than 2, right? The little caret thing? Or...
This thing right under clear. Everyone see that? Alright, Ian, what does your graph look like for this third one? It looks like that. Okay. Okay. Write it in. So the third one, is this kind of simple, guys? Let me see this stuff. How many, what's the degree for this equation? 4, the highest degree is 4. Everyone agree? Number of turning points? 1, 2, 3. Yes? Alright. Let's look at the last one. Do you change it or keep it the same? Ms. Sawyers. Did you change it or keep it the same?
The last problem?
Yeah, you kept it. Alright, so.
I meant to change it.
4. Will you put a, I don't
Yeah, I
maybe
know.
you
I
were-
wanted to change the order and I didn't.
I'm like, maybe you're sketching the graph in the wrong spot.
Fell asleep.
Fell asleep. Your hand just went. Alright. And for this 4th one, everyone should get something that looks like this. Does everyone see that? It's weird, right? So it kind of loops down, comes up here. Alright, what's the degree of this equation? What is it? 4. Okay, so the maximum number of turning points could be what? 1 less than the degree, which is 3. Yes? Is everyone with me? But in this picture, I definitely see a turning point here. But I don't think I see anything else because this is constantly increasing. Everyone see that? It swirls, but it's going up. Okay? So how many turning points are here? 1 turning point. So that's why when we're talking about turning points and we say the maximum number of turning points is 1 less than the degree, because it could be 3, 2, 1, it just depends on what the function is. Okay? Tricky, but you have a calculator. So you can always look at the picture. Good? Alright. Look at the bottom part. How many turning points does each of these graphs have? So, how many turning points are here? 1, 2. Okay? What about this one? 1, 2, 3, 4. You guys did this already? Am I going slow? 1, 2, 3. 2, 3, 4. Yeah, be careful with that. Alright. Now the next question is going to ask us, is the degree even or odd? So we have to think about this. Is the degree even or odd? Let me do a special example in a second. So remember, based on the degree, the maximum number of turning points would be 1 less than the degree. So now we're going opposite. Okay? So if there are 2 turning points, this is an odd degree. And I'm going to bring it all together in 1 second so you can see easily. So this is 4. So if I went up 1, it would be x to the 5th. God bless you. That would be odd. What about this one? Does everyone see that? So 3, if I went up a degree, it would be to the 4th. So this is even. And then what about this one? Odd. Okay. Does anyone see a pattern? And I'll help you out.
What's different for the third graph than the other 3? What's different?
The end behavior. Look at the end behavior. What do you notice about this end behavior?
Opposite.
Opposite. This one. This one. Same direction. Last one. Okay? So, what can we conclude? When they go opposite directions, the degree of the function is going to be odd. When they go in the same direction, either both up or both, they're going to be even. Huge concept. If you can get that, you're good. Okay? Let's look at this last example. So they want to know the number of turning points here. Does anyone see any turning points there? It's just constantly what? Constantly increasing. It does not change direction. Right? If you go like this, I'm not changing direction at all. Constantly increasing. Okay? So my number of turning points is 0. But because of this graph, we need to know the types of functions we have. Okay? This would be a third degree polynomial, which we call a cubic function. Okay?
So you have to recognize the shape for cubic functions.
And so one of the questions that a lot of students will say is like, well, cubic and quintic look very similar. You'll be able to tell, okay, once we start studying this a little more, right? We call this a triple root. Just if you want to put a little note, just write in here, triple root. Okay, we'll talk about that more. Everyone good so far? Am I boring? Yeah. Alright, so here, exactly what we just talked about for end behavior, the conclusions and rules that we just discussed. So if it's an even degree, the end behavior is in the same direction. Okay? So same direction. So if you want, you can draw an example, like both up and both down, whatever. Give yourself some notes that make sense to you. And if it's an odd degree, we said that end behavior is in different directions, or opposite directions. And I'm just giving myself some examples, just random graphs. Okay? Sometimes it helps make the visual. Okay, so there's some things that we need to know before we practice some of this stuff. Okay, so we already know if the highest degree is even, they're going to both go in the same direction. We know that if it's in odd degree, it's going to go in opposite directions. But the question is, if it's even, how do I know if they're both going up or if they're both going down? Okay, and it's one extra piece to this. The term with the highest degree, okay, meaning the largest exponent, you need to look at the coefficient and see if it's positive or negative, okay? So let's look at this one as an example, okay? It says the degree. What is the degree of this function? 2. Highest degree is 2. That's what we mean by degree, okay? What do we call this? If it's x to the second? Quadratic. Okay, so you guys know this. What's the number of possible terms? Just one. Okay. Now, remember our quadratic function. This is just a sketch of what my parent function looks like, right? Think about your transformations and if there's a negative in front. What does that do to my function? It reflects it downwards, right? So because this leading coefficient is a negative, both my arrows are going to go down. When it's positive, both my arrows go, that's it, okay? So as x approaches positive infinity, they're both going down. So what would y be approaching? Negative infinity. And as x approaches negative infinity that way, since both arrows are going down, my y value is approaching negative infinity. Okay? So evens are a little bit easier than odds.
What if you don't remember, what if you can't remember that? Because I can guarantee 90% of you are not going to remember this concept. What could you do? Yeah, just put it in the calculator. You guys know how to do in behavior. We've been doing in behavior since the beginning of September. So this really isn't new. So don't feel overwhelmed by conceptual concepts.
So what about this one? What's the highest degree? What's the degree? 4. What do we call that? Linear, quadratic, cubic? Quartic. Quartic. So to the 4th is quartic. Number of possible terms? 1 less than the degree. 3. And then the highest degree is 4, and it's a positive leading coefficient. So where do you think both my arrows are going? Up. And what's up? Okay? Everyone okay? Alright. Next one, what's the degree? What do we call that? Quintic. Linear, quadratic, cubic, quartic, quintic. Linear, quadratic, cubic, quartic, quintic. Say it. Number of possible terms. 1 less than the degree is 4. Okay. So again, these are hard to memorize. So go into the calculator and see if you can see what it looks like. Okay. So go ahead. Type it in. Two x to the 5th minus 3x. Okay, that's going to show us our end behavior. How many turning points do I have? 2. I just have 2. But where it says number of possible turns, they just want to see 1 less than the degree. So, as x is approaching positive infinity, where is this end going? Positive. As x is approaching negative infinity this way, it's approaching negative. And they're going to be opposite. Okay, we know odd is opposite. So if you get one end behavior, you know the other. It's really that simple. All right, try the next one. Without me. You guys are really quiet today. What? You want me again? Beggars can't be choosers. So I'll take the 2.5 days we had off. So this is what your picture should look like. Once you get your answer, you can check it off of mine. How do I pause this, Miss Sawyers?
You click on the whole thing.
This round thing?
Oh yeah, you can try that. Yeah. If you
Why are you trying to
sorry, if you see when it turns to a plus, if you click it, and like just slide it. Oh no, come on. There it goes.
Oh, okay. All right, so function family. Function family. So the first thing I look at is I look at the end behavior here and I say, oh, this has got to be even, right? Okay, the next thing I say to myself is, how many turning points do I have here? So I start going 1, 2, 3. So what do we think the degree could be? It's 3 turning points. We go up 1. 4th, right? Okay, so on the side I'm just going to write f of x equals x to the 4th. What do we call that, x to the 4th? Quartic, okay? So specifically we call this a quartic function. Do you want them to say polynomial or do you want them to be specific?
If they can be specific, that's great. But if they just put polynomial, I won't count it wrong.
You guys should know the names. But Miss Sawyers is really nice. So she said you can put polynomial. If I was grading it, I'd make you put exactly what it is. Okay, is everyone okay with that? Ryan? Likely classification by the degree. We said x to the 4th, right? Which is a quartic. So f of x equals x to the 4th, quartic. Who can tell me what my domain is? It goes up and out. Excellent, both of you, good job. Negative infinity to positive infinity. Questions on that? Okay. Fernando, do you think you could try the range? I'm going to help you through it. So you said -4 to what?
Bracket.
Right, bracket, that's okay, I like what you said. -4 to what? Excellent, very good. -4 to positive infinity. Questions on that? Don't be afraid to ask. Okay. I'm going to skip interval of increase and decrease right now. We'll do the hard ones last. I just like to get the easy ones out of the way. Does anyone know what the zeros are? Right, where the graph goes through the x-axis, right? So x equals what? -1, -2, -3. So somewhere in between -2 and -3, closer to -3. So -2.8. Ian, you like that one? I like that number too. I would put that. What about this one? Someone who hasn't spoken to me. What's this 0? Don't say 1. It's not on 1. But it's between 0 and 1. 0.7. That's what this is. X equals 0.7. Okay? So then my x-intercept should be easy once I have that, right? Why should it be easy? Because it's the same thing. We just write it as a point. -2.8, comma 0. 0.7, comma 0. Questions? All right, Junior, how many turning points are here?
3.
Excellent. Who can tell me the y-intercepts? Where the graph goes through the y-axis. How many are there? Uno. Arlene, you want to tell me?
0, -1.
Beautiful. 0, -1. Questions? Okay, easy one. Are there any asymptotes here? No. We haven't really done many asymptotes. Not for polynomial functions. End behavior? Where are both my arrows going? So where's that? Both to positive infinity. Okay? So we knocked out the easy ones first. Good? Alright. Interval of increase and decrease. This is where most of us have problems. Okay, so I'm going to take it kind of slow. From left to right. Left to right. We're going to follow the graph and we're going to determine if it's increasing or decreasing. So from here. Decrease. So I'm going to put a D. Probably use a different color. Okay. To the turning point, then what starts happening? To the turning point, what happens? And then, okay. So first step, label increasing and decreasing. Good? Yes? Jay? Okay. Next step. Intervals of increase and decrease are the x values. X values. So everywhere where I stop, I want to label the x values so that it's very easy to just figure it out. Okay? Who can tell me what the x value is for this point? X value. X. So Beatrice said it's approximately -2. I would say -2.1. Do you see how it's not exactly on -2 right there? Okay. So do -2.1. If it's not exact, try to stay away from being exact. Okay? Any questions on the x value there? Everyone good? What about my next x value? What's this one? -0.5. I'll take it. And then, what about my x value here? X value. What is it? 0.2. We'll go with Ian. 0.2. Perfect. Okay? Everyone okay with that? So first, from left to right, we're going to label it decreasing or increasing. Then we're going to label all our x values. Okay? Now, I start decreasing. From left to right, so decrease. Where is this decreasing from? Negative what? Where does it start? Negative infinity, and I go to what x value? -2.1. That's my first interval of decrease. What do I start doing from here? Increasing. So that's going to be the beginning of my interval of increase. So -2.1 to what number? -0.5. From -0.5, what do I start doing? Decreasing. From this x value to this x value. So you write it as a point. As a interval. Not a point. So from -0.5 to 0.2. Then what do I start doing from 0.2? Increasing. Maximum stays at 0.2. And we increase to positive infinity. Not because I'm going up, but because I'm going out. Okay, x values. Questions? I don't need that. I hit it too fast. Okay, anyone still need this? Okay. Good? Alright. Transformations of polynomial functions. So remember, given that f of x equals blah, 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 who can remind me what this back number does? Remember the number on the outside of the parentheses. So if it's plus, what does it do? The number on the outside. It goes where? You're right, Robert. Up. No, no, you're wrong. You're right. And then if it's minus, it goes down. Okay? My trick for memorizing these is memorize one, and then you know the other. Okay? That's it. The number on the inside. Remember we always say insiders lie? Did we say that in this class? Okay. So if it's plus on the inside, where does that go? Left. And if it's minus on the inside, it goes to the right. So I always think about the number line for this one. And I think, oh, positive is that way on the number line. But insiders lie. So I have to remember it goes to the left. If that confuses you, ignore me. All right. No, okay. Your A value, you guys remember this? Your A value. So if it's between 0 and 1, what happens? Is it a vertical stretch or a compression? Compression. So this is a vertical compression. I remember I showed you guys the rubber band thing. They said if it's like a fraction in the front, less than 1, it makes it fatter, wider. That's what a vertical compression is, when it flattens it. Okay? That happens to make the function wider. And then if A is greater than 1, then what is it? A vertical stretch. And again, you can always use a calculator for these things, but you've got to have something. You got to know some things about it. Okay? And then the other part is if there's a negative in the front of the function, in front of the A right here, what does that do to my function? What does the negative do? Flips it over what? Over the x-axis. So I'm going to write reflects over x-axis. Questions? That's supposed to be a negative. And it just looks like a... You guys kind of remember that? Yes? Somewhat? Alright, so, what do we call this? X to the 4th. What's the name of this? Linear, quadratic, cubic? Quartic. Quartic. Quintic is 5. So f of x equals x to the 4th is quartic. Quartic. Write it down if you can't remember it. Remember that our quartic function looks like our quadratic, but it's a little bit flatter, right? Does everyone see it's like a little bit flatter there than our quadratic? If you typed it into the calculator and you did y equals x to the 2nd, and you did this y2 equals x to the 4th, you'd see the difference, okay? What's the transformation here? Does anyone see? It's a negative quartic function. There's a negative in the front. What did we say a negative does? Reflects it over the x-axis. That's it. So if I'm sketching this, I'm just taking this function and I'm flipping it downwards. Okay? So it just looks like this. Flat here and reflecting it downwards. Literally, that's it. You guys okay with that? What about the next one? Who can tell me what the transformation is? First of all, it's x to the 3rd. What do we call that? Cubic. Write it down so you can remember it. Cubic. Linear, quadratic, cubic, quartic, quintic. Linear, quadratic, cubic, quartic, quintic. Okay. What happened here? Someone. Anyone. Plus 2 on the outside. So on the outside. 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 Where does it go? Up 2. When you're working with a cubic function, okay, use this point as this part that you move. Okay? So I'm literally just taking this function and moving it from here up 2. Okay? So where Jennifer Mill starts, right here. I put that flat part because that's up 2, and then I just copy the way that the graph goes. It goes here, and it goes here. Okay? Remember, these are just sketches. They don't have to be perfect. The next page has to be perfect, but this doesn't have to be perfect. Questions? Is everyone okay? X to the fifth, what do we call that? Quintic. Quintic. Linear, quadratic, cubic, quartic, quintic. Okay. Again, remember, here's my cubic. It's a little flat there. This is even flatter, my x to the fifth. Okay? Who can tell me what the transformations are here? A -3 on the outside. What does that do? On the outside, down 3. And what about a -1 on the inside? Right 1. Okay? And notice what I'm doing. I'm looking at the function. I'm pulling out the pieces. I'm writing down what I have to do. And then I'll sketch it. Okay? So, again, you're taking this flat piece right here. And you're moving it down 3. 1, 2, 3. And right 1. So that flat part should be right there. Does everyone agree with me? Okay? And then I just copied the way the picture is drawn. It's just a sketch. Questions? Alright. Everyone's got that? Flip the page. Hopefully quiet when we have the class here. Alright. So I'm going to do one with you. Make you guys do the next one on your own. You okay with that? Yeah. Alright. Which one do you want me to do? Graph all the following polynomial functions. Label all important points, including intercepts and turning points, where necessary around 2 decimal places. Which one looks harder, A or B? A or B? Raise your hand for A. Raise your hand for B. Alright, so let's do B. Okay? Now, this is actually written in vertex form, so it's you can see all the transformation. Okay, it's squared. So that's your quadratic. You have your transformations. You can see it. So this you could technically do without a calculator. You don't have to, but you should. This one, it's cubic, brand new. Maybe we should graph it. So everyone go ahead into the calculator. Let's start there. Go into y equals, and we're going to type this in. Make sure you put in negative, not a minus. Okay, to get that 3, I hit the caret under clear. I always say to the third, and then you have to push to the right to get you back to regular numbers. Go ahead and hit graph. Then it looks something like this. Now, they're asking us to label important points. So we need specific points here. We can't just sketch this. Okay? So if you hit second graph, this is going to give you a bunch of numbers. Okay? Do I want to plot -3, 63? Do I want to plot that on this graph? Why not? It's not on the graph. The graph only goes up to 10 and -10. Does everyone see that? So you got to find numbers that fall on this graph. -1 and 5. 0, 0. 1, 3. 2, 8. 3, 9. Hello.
Is it done?
4, 0.
Yeah.
And that's it. So I have a bunch of these.
Yes, that will be.
Did you get the same one? You put minor? Did everyone get the same numbers as me? Do I get different numbers? Do I have a different one? Right? Anyone else get a different numbers? You did? Check the function. Make sure it says negative x to the third. Remember, we're doing B. What was the problem?
Their table setup, hers was jumping by 8s instead of going by 1 in the table.
Well, aren't you a lucky winner today? Alright, everyone okay with that? If you're not, let us know so we can check.
Good morning. This is Mr. McMahon again. Please pardon the interruption. Teachers, this morning's presentation in Springbank Auditorium is complete and students are returning to class. Thank you, West Potomac. Have a great day.
So if you're just getting back, if you could get your packet back out, and we are actually just starting this is the perfect time to come back. We're doing B. This one over here. And grab a calculator.
Alright. So, based on my graph, I'm just going to sketch it from all these points that I have now. Okay? So I see that it's... I know, I am.
Good morning, I'm just dropping off things. Sorry.
So I see that it's going like this, it comes up, here, comes back down. Is everyone okay with that? So they want me to label intercepts. Can anyone see what my intercepts were? You could look at the table if you need to. Well, what was this intercept right here? 0, 0. Right? Anything where the y value is 0, I should have 2 of them. And then what was this one? 4, 0. Excellent. Yep. Now, these are my x-intercepts. Does anyone remember what the y-intercept one is? Y-intercept where the graph goes through the y-axis. What's that one? It's also 0, 0. Okay, so the blue are my x-intercepts. The green is my y-intercepts. They also want me to label turning points. How many turning points do I have? 2 turning points. Okay, do not go based off of the graph. We've got to go based off of the calculator. Okay, because remember, even though I got these points, I don't know for sure that that's the turning point. Okay, so we're going to practice it in the calculator. 1 turning point here, I'm just going to write TP, is 0, 0. Okay. Do you guys remember how to check this? What do we call this? It's a turning point, a vertex, or a max or min. What is this one considered? Minimum. The lowest point. Minimum. So, if you don't remember this, follow along with me. Second, trace. I want minimum, so I choose 3. Okay, practice this in the calculator. Because in this unit, you could have 4 turning points that you need to find. Okay? This is my minimum. It says go to the left of the minimum. Well, it's kind of blinking exactly where I think that minimum is. So I'm just going to hit to the left a little bit. Does everyone see how my cursor's to the left? You hit enter. Okay? Then it says right bound. This is where I think my minimum is. I'm going to go to the right of that point. So I'm just going to go here and hit enter. Notice how it gives me these 2 arrows? Because what it's saying is, your minimum is somewhere in here, and this is where I'm going to check to find where your minimum is. The guess is just, well, I think it's right here. And I hit enter. And it gives me exactly what my minimum is. Now remember, looking at the calculator, do you guys see how there's a letter in this number? Do you remember what it is if you get an E there? It means 0. It means 0. I don't know. You can call Texas Instruments and complain to them. Okay? So this is actually 0, 0 because e to the negative 6, Scientific notation. 0.00000000000. Okay, so good. 0, 0. Perfect. Next one. Is that a max or min? A what? A maximum. Second trace. 4. Okay. Oop, what did I do? Second trace 4. Okay. So I think my maximum is right here. I always start where I think it is. It says go to the left of the maximum. Left, 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 left. Hit enter. This is where I think my max is. It says go to the right of it. Right, 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 right. Enter. See my arrows? Austin, you see those?
Yeah.
It's checking right between here for my maximum. Okay? If you ever have your arrows crossed, your arrow's too close, it's not going to work. You're going to get an error. Okay? So my guess is right here. Enter. And I'm going to round this 2 decimal places. So who can tell me what this turning point is? 2.6 what? 2 decimal places. 2.67, comma, 9 point. 2 decimal places.
Oh.
9.40. Excellent. Questions? Comments? Concerns? Okay. How do I do this now? Alright, so for A, God bless you. In y equals, make sure you have your function typed in properly. Okay? In y2, you can put 0. That way we can find the intercepts very easily. Look at your graph. Make sure you know what it looks like. To graph it, you go to second graph, and it gives you a table. Remember, I don't want to plot these negative 223. It's off of the graph. So I would plot 0, 7. I would plot 1, 2. 2, negative 1. 3, negative 2. 4, negative 1. 5, 2. 6, 7. Okay? And then I'm just going to connect the dots. Alright, so it's asking for all of the important parts. It's a terrible graph. Oh. Alright, so the vertex, turning point, what do we call it? Is it a max or min? It's a minimum. Second trace, minimum, to the left of it, to the right of it, and my guess. 3, negative 2. Okay? So my turning point, 3, negative 2. If you're having trouble with that, make sure you see us during Wolverine time. Alright, x-intercept and y-intercept. So x-intercept, we already have it set up, where we have in y2, we have the 0. So if I hit second trace 5, which is intersect, okay, remember the first y equals is graphing this quadratic. The second y equals is graphing the x-axis. So I'm looking for my intersections right on the x-axis, okay, which are my zeros. Enter, 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 and I get this ugly number. Doesn't matter that it's ugly, that's the intersection, okay? So x-intercept is 1.5 what if I'm rounding 2 decimal places? 1.59, comma 0. And then the other one, second trace 5. Go to the other intersection. Enter, enter, enter. How do I write this? What's this? Thank you. 4.41, comma 0. Questions? Who remembers how to get the y-intercept? Second trace value. Good job, Junior. Second trace value. And this one's cool because it just says, well, x equals what? Well, for my y-intercept, x always equals. So I type 0, I hit enter, boom, gives me my point. 0, comma 7. What do you think? Easy, hard, medium. Easy? Medium for anybody? Hard for anybody? If it is, come and practice with us, okay? All right. Let's knock these out so we can do some factoring practice. Identify the transformations applied to the function y equals x to the 24th that results in this function. All they are asking you for are the transformations. Do I care that the parent function is y equals x to the 24th? No. The only reason I would need that is if they were asking me for end behavior. Okay? That would be the only helpful thing. In this case, it is literally just transformations. How many transformations do you guys see here? How many? 3? Does everybody see 3? Someone give me 1. Down 67. I would start from the back because I think it's easier too. Down 67. Someone else. Left 12. Good job, guys. Right there. Left 12 units. Does anyone see the last transformation? The negative, right? The negative in the front. So that's a what? We said a reflection in what? Reflection over the x-axis. Should be rolling off your tongue. Number 3, identify the transformations applied to the function y equals x to the 68 that results in blah, 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 blah. Who can give me a transformation? Someone who hasn't spoken to me yet. You spoke to me already. That's like me. Up 12. Thank you, Junior. Up 12 units. Up 12 units. Anyone else? Give me another one. Right 14. Good job, guys. Right 14 right there. Right 14 units. Now, this -2 in the front. Look at it as 2 separate transformations. Flip over the x-axis. Vertical stretch. Vertical stretch. So, the negative, we're used to that one, so I'm going to say reflects over x-axis. And then remember, when you look at the number, we need to see if it's between 0 and 1, it's a vertical compression. If it's greater than 1, it's a vertical stretch. Okay? So this 2 is a vertical stretch. And what you might see on tests, SOL, stuff like this, you might hear it as a vertical stretch by a factor of 2. So again, as long as you know it's a vertical stretch, you're good. Sometimes they use that wording by a factor of 2. Okay, whatever the number is, they'll say it like that. Okay, so I'm just exposing you guys to that. Alright, you try this last one. Polynomial. Polynomial. 4 or more terms is a polynomial. Okay. 4 terms, we always use grouping. Alright? So, I'm going to group the first 2 terms with the second 2 terms. Okay? So 4 terms, we use grouping. And the way we start with grouping is GCF. Okay? What is the GCF for PR and 2P? What do both of them have in common? P. P. For pretty. Mrs. Mills is pretty. Alright, so I pull out P. What am I left with? R minus 2. Fantastic. Questions about that? Remember when you're pulling the GCF out, it's technically like dividing it out of each of those terms. Okay? This next one. 7R and negative 14. Or we could just say 14. What does that have in common? 7. So I'm going to write plus 7. And what am I left with? R minus 2. Now, for grouping, you want to make sure that both of these are the same. Okay? So if you were able to get the first one, you could have said, well, for this to work, for this to be factorable, this middle term had to be the same here. Okay? So you can think of it like that if that helps. If it doesn't, ignore me. Perfect. Now, we have the r minus 2. So we've used that. You only write it once. What am I left with? Does everyone see this? P plus 7. And you've just factored this by grouping. Okay, ask questions. Anything that doesn't make sense, anything that looks funky, something you don't understand. Anything. Alright, pick one more. 1, 2, 3, or 5. 3. Seriously.
Let's do one. We haven't done one as a class.
One?
I don't think.
Does everyone know how to do 3?
Yeah, you can put it in.
You can put it in the calculator. So remember, in y equals, I'm not going to, well, I guess I can. 25 divided by x, and then in y2, 25 divided by x plus x. Then what do you hit? Second graph. And then you look in the last column for what? The middle term, which is 10. Okay, the first one, this one's a better choice. Okay. 27y to the third plus 8. Because it's 2 terms, it could be difference of squares, difference of cubes, or sum of cubes, or GCF. Is there a GCF here between 27y to the third and 8? No, doesn't work. Difference means what? What should be in the middle if it's a difference? A subtraction sign. So this has to be the sum of cubes. There is no such thing as the sum of perfect squares. We'll point out. Okay? Sum of cubes. Everyone okay with that? Okay. So, sum of cubes. Remember it has this formula? Does everyone remember this formula or no? Formula. Okay. A plus B, same. Opposite, I always have to do the signs first. Same. Opposite, always positive. If you can't remember the formula but know the process, that's okay. I'm just writing it there so we have a guide. Okay, for those of you that don't remember. Okay. What Jennifer Mills does when she answers these questions is because I know it's cubes, I say to myself, what is the perfect cube of each of these terms? That's how I get my A and B term. Okay? But to begin, gosh, I can't keep it straight here and there. I always start with the signs. Always. So sum. Same. Opposite. Always positive. Guess what? On many tests, on SOLs, on quizzes, if it's multiple choice and you know the signs, most of the time you're going to get it right just from there. Okay? Now I do my cube things quickly. Cube root of 27y to the third is 3y, and the cube root of 8 is 2.
If you don't know, you're going to have to put it in the calculator.
I'm going fast because I want you guys to pack up before the bell. First term in my trinomial is my first term squared. So 9y squared, so I'm just squaring this. The middle term is both of these multiplied together, 6y. And the last term is the b term squared. That's it. Okay? Alright guys, once you have that, pack up, close the calculators.
You need to finish those last 3 for homework, please. I'll go over them at the beginning of next class.
And
Or Mrs.
remember,
Mills, if she's still here.
yes. And remember that if you were not here for the notes, just copy them down.